Welcome back to the Oxidation Reduction playlist on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In the previous set of videos, we talked about reducing agents in organic chemistry, particularly for carbon-oxygen bonds. We discussed the weak reducing agent, sodium borohydride, and we also discussed the stronger reducing agent, lithium aluminum hydride. In this video, we're going to look at a mixture of problems involving those, and then we're going to do a synthesis problem at the end to integrate multiple concepts from multiple chapters, including this one. All right, so to start off, we've got some 5 predict the products kind of questions. All right, so our first question, we have this ketone right here, and we're going to try to reduce it with sodium borohydride. We want to predict the product. Well, first of all, you should ask yourself, will sodium borohydride actually reduce the ketone? The answer is yes, it will. It'll basically take this carbon-oxygen double bond and reduce it into an alcohol. So our carbon skeleton stays the same, and this gets reduced into a simple OH. And that's our product right there. All right, fairly straightforward. One follow-up question I could ask is, can we still accomplish this transformation with LAH? And the answer is yes. We could also use lithium aluminum hydride, and we would get the same product, okay? Because anything that sodium borohydride can do, LAH can also do. It does not work in the reverse direction, as evidenced by the second one here. What functional group do we have here? So this is an ester. That's an ester. And the question is, will sodium borohydride reduce this ester? The answer is no. So I would actually put no reaction here. If I saw a question on an exam, you had an ester, sodium borohydride, I would put no reaction. I'm actually going to modify this a little bit. I'm going to modify it. I'm going to change this to LAH. I just put that so we could prove a point. All right. So let's use LAH and let's predict the product of this ester hydrolysis, okay? Or not hydrolysis, reduction, excuse me. All right, so how do we predict the products of an ester reduction by LAH? Well, remember this bond right here between the carbon and this oxygen, the single bond, we're essentially going to imagine splitting it like that, okay? And then whatever is on the oxygen side, we're just going to take that oxygen and throw a hydrogen on it. So that product, which I'm going to put in purple, is going to be this. I'm going to put it in the same orientation. There we go, like that. So methanol. Then I'm going to take the other side of it, which is, I'm going to do in light blue. That's the rest of it over here on the left side. All I'm going to do is I'm going to take the carbon-oxygen double bond and simply reduce it to an OH. And so remember, when I do ester reduction by LAH, I should get 2 alcohol products, okay? They do not have to be the same product, although in some cases they can be if the number of carbons on each side of the chain are the same. Okay? Here's another question. Here I have what looks like a ketone. So here is my ketone functional group. Will LAH reduce ketones? The answer is yes. Sodium borohydride could also do this transformation. So let's actually look at the carbon skeleton. There we go. And when I use LAH, or sodium borohydride for that matter, this carbon-oxygen double bond will be reduced into a simple alcohol. All right, there you have it. Okay, next, what functional group do I have here? This functional group looks to me like an amide, okay? I really didn't need to include this CH3, but that's an amide, okay? And does LAH reduce amides? Yes. Does sodium borohydride reduce amides? No. Now, what's the strategy we talked about for amide reduction in the last video? All we do is we find the amide functional group and just imagine chopping off that oxygen that's part of the carbon-oxygen double bond. Just imagine chopping that off, and then we just redraw the molecule basically without that oxygen. And that's all there is to it. You just imagine chopping it right off, and you end up with the amine version of that amide. Okay? Our last problem here is an aldehyde. Will LAH reduce aldehydes? And the answer is yes. So will sodium borohydride for that matter, and you'll get the same product. So I would take this carbon-oxygen double bond and simply reduce that into an alcohol. And that is my product of LAH reduction of an aldehyde. Now, for some of these, for example, this ester right here, this amide, if I had a carboxylic acid, same story, I have to use LAH. If I have a carbonyl-containing compound such as a ketone or an aldehyde, however, you can use either sodium borohydride or LAH in theory, right? In practice, you probably would want to use sodium borohydride. The reason you usually want to do that, unless you just want a tremendous yield, although the yield is still pretty good with sodium borohydride, is because lithium aluminum hydride can be explosive. It's very reactive, and it can cause a lot of problems if you don't use it correctly. My organic chemistry teacher, when I was in school, told us a story about how in his lab there was LAH that was used and there was an explosion of some kind, because I believe the reaction is very exergonic. Don't quote me on that, but I believe that's true. So, if you had a choice between sodium borohydride and LAH for this first one or this last one, you would probably choose sodium borohydride just for the sake of safety. All right? All right, now let's integrate some ultimate concepts together from multiple chapters. So we want to design a synthesis for the following molecule, beginning with acetylene. What is acetylene? This is a molecule you should learn by name and by structure. It is actually just a triple bond. And all it is a triple bond with, two carbons. So 2 carbons in a triple bond. In fact, let me redo this. Here we go. 2 carbons in a triple bond. That's all acetylene is. So a lot of times, a lot of synthesis problems will start with acetylene because acetylene in real life is actually very inexpensive and it's a good starting material. And on synthesis questions on exams, they like to ask beginning with acetylene. So we're going to start with that. We want to synthesize this molecule which is ethanol. Okay, so we're starting with acetylene. So we're going to have to think, we need to get to this compound right here. Now, there are no reactions directly, no alkyne addition reactions that can directly produce an alcohol. So that means we're going to have some number of intermediate steps. Well, let me think, what do I know that I can use to produce an alcohol from? Right? What can I produce an alcohol from? Well, I can produce it either from a carboxylic acid, or I can produce it from an aldehyde. Okay, in this case. So why don't I just try an aldehyde and see what happens? What's the corresponding aldehyde to ethanol? Well, it would look something like this, right? And I know the reagents to turn an aldehyde into this corresponding primary alcohol. I would just use sodium borohydride, okay? Now, do I know any ways to convert acetylene into this aldehyde? And the answer is yes if you've done the Alkyne chapter in your textbook. There's actually one reaction that you can do to do this. I mean, it's only one step. There's actually, because of the nature of this molecule, you can actually do 2 reactions to accomplish this. One of them that I can think to do is actually just do mercuric sulfate, so HgSO4, and sulfuric acid, H2. My pen's kind of messing up, H2SO4. This reaction is an alkyne addition reaction in which one of the carbon atoms, in the way I've drawn it, it's actually this one, just simply gets oxidized to a double bond oxygen, and the other carbon will pick up 2 hydrogens. Okay? And so this reaction of going from this alkyne, 2-carbon alkyne, to this 2-carbon aldehyde can be accomplished with sulfuric acid and mercuric sulfate. And then this aldehyde can be simply reduced into ethanol by use of sodium borohydride. Now, like I mentioned, we could also use lithium aluminum hydride here. We could do that, but we don't really want to use that necessarily because it's more prone to, I guess you could call it lab disasters. We'd much prefer to use sodium borohydride, okay? Although on an exam, I don't think this really makes a difference. Some people would actually just prefer to use LAH. Okay, so hopefully this makes a little bit of sense, and hopefully you got a little bit better understanding through this video of the various reductions that can happen on carbon-oxygen bonds. Thank you for watching this video. Make sure to like and subscribe, and join us in the next one where we go over DIBA, another reducing agent that's very important.